Very good question. So we would get to this operation in much more details very soon, don't worry, but there was one question that why we get, when we add them up together, we have two x3s, or over here we get two x6s, right? So remember that I said the coefficients of these polynomials are defined over z2, which means that every time that we add the coefficients together, we would compute modular 2 over the coefficients. So here we get 2x3. 2 is the coefficient. We compute mod 2. So 2 mod 2 is 0. So this one get cancelled, right? If there was like 3x3, then we would get just 1x3. If it was like 5x3, we would again get just 1x3 because the coefficients are only defined over z2, which can be either 0 or 1, right? Did I answer your question?
Just to rephrase it to make sure I understand, it's because we're operating over the mod 2 that every pair, like every not pair, even number would turn out in a 0, right?
Yes, yeah. We compute mod 2 over the coefficients. For example, if we had like 6x3, we would just get 0. We would cancel it because 6 mod 2 is 0, right? So we would not have it at all. Just small details, yeah, in case that you wondered around how did it happen. But I'm just gonna leave these details here, just like some small, imagine it was an advertisement of how these things worked out. I'm gonna also give you another example. Maybe I should make a page 24. So remember that for mixed columns, we define another variable under variable y, and then this is like 2 to the power 8, which means that we have the polynomials over. Let me just write it down. So we have f of 2 to the 8 over variable y 0 1. This h means hex representation, y to the 4 plus 0 1 hex representation. Okay, so these are saying that all the polynomials over f2 to the 8 with degree less than equal to 3. So why 3? Because the degree of this irreducible polynomial is 4. So any polynomial we choose, we divide it by this degree 4 polynomial. The remainder should be at least at most 3. So let me give you an example. I just provided these examples that later you come back after we go through polynomials thoroughly, and you come back over here, you have some examples to work on. Imagine I define two polynomials. I define y1 to be a3 y to the 3 plus 21 y2 plus 15 y1 plus e6, and then y2 I define it to be let me write them under each other. So 0 2 y2 plus a3. And imagine I have these two polynomials under this irreducible polynomial, and I just want to add them up together. So for those that forgot the hex representation, so 0 to 9 is 0 to 9. A is the representation of 1 0 1 0. B is the representation of 1 0 1 1. C is representation of 1 1 0 0. And then we have D, which is 1 1 0 1. And then we have E, which is 1 1 1 0. And then we have F, which is 1 1 1 1, right? These are just hex representations. So what I want to compute is y1 plus y2, which is equal to, so the first thing, we don't add anything, so a3, y3 comes up, plus we have 02 plus 0, 21 plus 02 hex. So let's see how do we do this computation. So we have to break them down into two pieces. So the first one we are XORing them with summation. So we have 0, 0, 1, 0 plus 0, 0, 0, 0. This is the first part. And then the second one is just 1, so 0, 0, 0, 1. And then the second part is 0, 0, 1, 0, right? 2. So when we XOR them, we get 0, 1, 0, 0, and then we get 0, 0, 1, 1. So we get the representation of 2, and then this is the representation of 3. So we get 23y2, okay? Plus, this one is 0, so we get itself 15y plus. So now we want to do this next computation, so I just write it down here. So we have E. Remember that we show E like this one, 1110. So 1110 plus A, which is 1010. And then we have 6, which is 0110. And then we have 3, which is 0011, right? So we XOR them together, so we get 1, 0, 1, I'm sorry, yeah, 0. And then over here we have 0, 0, 1, 0. So together, this is the representation. If you want to show it with hex, this binary is representation. So it would show, it is showing nothing by 4. And this one is showing 5. So it would be 4 and 5 in hex representation. All of them are in hex. So again, we have to do this one, mod 0, 1 y4 plus 0, 1. Then actually the result would not change. Again, it would become the same thing because the degree is less than 4, so the modular operation doesn't come to play at all. So you may wonder around that why do we use this operation? So remember that in mixed colon operation, we said that we are working with the words. So we have a colon that it comes to the game, and very soon I think we will go to an example. But I think now we have enough background of what is going on in the background. Now we can go ahead and talk about substitution byte and see what is happening there. So in the substitution byte, we have two functions that are happening at the same time, f and then g. So the f function, so as you see that substitution box of this input x is g of f of x, which means that we compute f of x first, and then we, whatever value we get, we substitute it to compute j of that value. How do we compute f of x? What is the f function? So the f function is nothing but just computing the inverse of this value. So for any value x, find for x, find multiplicative inverse such that x times, this multiplicative inverse becomes 1, mod that polynomial, right? So for example, let me go back. If this is our polynomial, x8 e to the power of x4, and this is it, this is our field. If I give you the input is x3 plus x, and the output of the x function would be x5 plus x3 plus 1. Why? Because if I multiply these two polynomials to each other, I get 1, right? So from that computation, every time that the f function receives this polynomial, it would output this other polynomial because these are the inverse of each other. How do we compute that? Soon we will get there to see how do we compute it. That is not our issue at the moment. All right, so that is just returning the multiplicative inverse. And it is done under this polynomial. So once we've done that, the G is actually just a linear combination. So we would receive that multiplicative inverse, and we would multiply it to A, and then we add B to it. So then we are basically computing AX plus B. So something is very interesting in the world of multiplicative inverses. The multiplicative inverse of any element in mod a polynomial or mod P is unique. And when I ask you what is the multiplicative inverse of this element, it is always this under this given polynomial, irreducible polynomial. And if I give you this one and I ask you what is the inverse of this, so the algorithm would always output this one. So which means that multiplicative inverse is inversible. So it is important because when we want to compute the decryption of some value in the DES, we know that the substitution byte would take this operation, but it is also important for us to see if substitution byte is inversible. If it is not inversible, it means that we are not able to do decryption at all. So let me show you that G function. I think G is a little bit weird over here. So G is nothing but a linear transformation, which is defined by AX plus B. A is a matrix that of polynomials, and then remember we show the polynomials with bytes, 1, 1, 1, for example, and so on and so forth. So we have a matrix of them. And then B is just one polynomial, 0, 0, 0, 1, 1, 0, for example. And then now you understand that when I'm saying AX plus B, whatever polynomial you put there, or value you put over here, you can just compute this whole thing, the AX plus B, right? And then you can immediately compute the output. So this is just a linear computation. So we know that from this construction. So again, one more time, I go through this. So in order to compute the substitution box, the substitution box has two parts. The first part, we have to compute the inverse of the input polynomial, input byte. We know that there's an algorithm later, we discuss it, that we'll find it, and it is inversible. Once we find this, we would input that one to this linear transformation. So we compute A is a fixed matrix, it is given. B is also a fixed metric, it is given. So we take this x minus 1 and we would substitute it with this x over here, and we would just compute this linear transformation. And done, that's it. So we are now we have computed this all computation for substitution byte. The only thing remains to see if this G is inversible or not, or reversible. That is the question that we have. So let's see. Let me define C equals to A. Remember that we always put the inverse of X, multiplicative inverse of X. So C plus 1. Maybe I can put this one over here. Inverse of X. That now it makes sense over here. So now I get this whatever value that is the output, I define it to be C, and then my goal is to see if I can use that one to get back to the X, right? So suppose that C is my output. So what I can do to do this computation now, what I can do is that I can return C over here and do some moving some of these variables. I can get x minus 1 equals to a minus 1 inverse of a, and then c minus b, right? I know that c is a vector, b is a vector, a is a matrix, and I compute the inverse of it, and so therefore I can compute it. So this means that yes, is G inversible? Yes, G is inversible, irreversible, or I should say inversible, sorry. Right? And then I know that I can compute the inverse of F. So is F inversible? The answer is yes, right? Because I can always compute the multiplicative inverse of X, right? So that means that I always, whatever the value I get over here, I can compute the inverse of A. So another way that I can show that one is that X, for the entire equation, I can return X as inverse of A, C minus B, and then the reverse of this entire thing, right? So I can return X. So we show that substitution byte would, convert some X value to some C value, and then given that C, I can reverse the entire operations so that I can, return F. So, so therefore the substitution byte is reversible. So, and then we have no problem, reversible. We have no problem with that. Another operation that we've been talking about is shift rows. That again, I have this sort of representation. So we said that we have 1 shift, 2 shift, and 3 shifts. And I think this should be clear by now how this operation works. Let's move on to the next one, which is our mixed columns. And I said that for mixed columns, we are going to use another polynomial that is defined over variable. Let me just use X over here too. This reducible polynomial X4 plus X, right? So what we are trying to do over here is that we are trying to represent every word in this matrix as if this one is A0, A1, A2, and A3. I want to convert this one to the corresponding state with values B0, B1, B2, and B3. So let's see how do we do that. So when I look at the state, this is my state. We said we are looking into the columns. So any of these values are 8 bits, 1 byte, which I can use them. They are a member of 2 to the 8. I can represent them as these hex values, any of this A0, A1, A2, A3. So then I form a polynomial. And then A0, A1, A2, A3 would be the coefficients of this polynomial. Okay. And then there is many different functions, C's that are also polynomials. And the way that we would do this conversion is that I would compute B of X equals to, I do this multiplication under this modular this irreducible polynomial. So, going back, I think I already discussed this case. Of course, this is under different polynomial, but imagine that we have again these 2 polynomials. We multiply them together. Instead of this dividing by this polynomial, I would divide it with the other polynomial, with this one, 0,1 hex x4 plus 0,1 hex, right? The operation would remain mostly the same. We don't have to really go into the details for that. So in order to do these operations all at the same time, so this is just one of the C operations. So I would define B0, B1, B2, and B3 to be as following. There is a fixed function 0, 2. These values are in hex 0, 3, 0, 1, 0, 1, and then there is 0, 1, 0, 1, 0, 3, 0, 2, 0, 1, 0, 1, 0, 3, 0, 2, 0, 1, 3, 0, 2. Okay, these are all hex values, and then you're gonna multiply them, imagining that that column is a polynomial, A0, A1, A2, and A3. When we multiply them together with this fixed polynomial, then modular that polynomial that we have here, 0, 1, hex 4, 0, 1, x4 plus 0, 1. Okay. After we do this multiplication, then we are able to do to get this b, and then we're gonna apply this multiplication to every column that we have over here, and then we can compute the corresponding b's on the other side. So that is given. So this is just like the computation that we have to do for the mixed column. And then we are going to discuss that mixed column is also invertible. So this is the computation. We are going to discuss that mixed columns is invertible. This is very important again for the decryption. So you may wonder, why are we choosing these different values or these c's? These are some polynomials that we call them cx that are these polynomials, and let's say just that this one is relatively prime to or irreducible polynomial is that we would show them in mathematics. We would show them they are co-prime with 0, 1, x4 plus 1. So what does that mean? According to the theorem that we have, when two polynomials are co-prime with each other, they are relatively prime. So which means that there is always a polynomial d of x such that c of x times d of x becomes 1 mod 0, 1 x4 plus 0, 1. So this is the key over here. So because we choose this c of x as these polynomials to be co-prime to this polynomial. Again, what is co-prime? We'll get back to that very soon in the next chapter. But just like remember that whenever these values, you choose some polynomials that are co-prime, then their inverse always exists. And because their inverse exists, then we can always cancel them out. So which means that we can compute a of x from b of x, right? Remember that after we do this computation, the result, we call it to be b. So how is so? Because we said that b of x is nothing but a of x multiplies to c of x, right? So now we know that d of x is multiplicative inverse of cx, Therefore, if we compute b of x multiplied to d of x, what do we get? We get a of x times c of x multiplied to d of x. We know these two would get cancelled to 1, and therefore it is equal to a of x, right? So therefore, the mixed columns operation in the DES is also reversible, okay? So I understand that these are a little bit too much in one session, but trust me, when we get back to the next chapter, and we will have a lot of examples, and these things would become very easy for you once you really understand the idea behind them. All right. So the next operation that we want to discuss is the add key. Actually, add key is one of the most simplest way. And we discussed that we would just add the round key. And after adding the round key, the operation would be very easy because we are just executing the operations. So if I go back to the algorithm, this red one is the definition of the add key. So we have the round key. We would just XOR the corresponding bytes and we would write the result into the state. So this is a very simple operation. All right, I think this is it for the AES. But there is nothing better but a very good graphical representation of this algorithm. Can you guys see my screen? Yeah?
Yes.
Yes. Okay, so let me show you in a graphical way how AES works. I think this will really help us to understand this algorithm better. All right, I'll pause it time by time to give you explanation. So this is the algorithm. You get the plaintext key and then you get the ciphertext. So this is how the key is filled. Remember that they fill it up from the top to the down. So if I go back, you see that the way that both key and the ciphertext are filled column by column. So every value over here is a hexadecimal representation of that byte. So we know that this is 8 bits, so we can show it as a hex. So our input, this comes from the message. So we fill it out with the state. And also we said that we have at least 128 bit of keys. So we also write down the key into another sort of ciphertext key state. And then now we have to do two sort of computation. So we have two stages. Yeah, so we have two operations. This one would go to the encryption algorithm. But before we go to the encryption algorithm, we need to expand the key to different round keys that we need, and we got them the operation B. So let's suppose we have this B. We would get back to this at the end. Let's just go. Suppose we already have our round keys, and let's see how the process A works. So as you could see, if I stop it right. So we already have the round keys, so initial round, so they are already given. Now this is the states that comes in. The first round we said we don't have anything, we just add the round key, and then for many rounds we would apply this 4 operations, and the last round is just a slightly modification of normal round. We do everything except that we don't do a mixed column. The reason for that is because it should be reversible. So that is why the last round is missing the mixed columns. So you see the round number over here. And then the round 10, we do these 3 operations and then we are done. So substitution byte, remember we discussed about the polynomial, irreducible polynomials and all those computation. And it turned out that, because we are having a fixed number of polynomials that we can show with 8 bytes, actually it is just 2 to the power 8 different polynomials. So in actual implementation of the AES, we don't do those TDS computation. We have pre-computed this table with all possible inputs. And then we are basically and literally doing a substitution byte. So we would just take any input and then we would break it down. The first one shows the row, the second one shows the column, and then we would substitute it with that. So this is equivalent of, computing that f function and g function and all those, reducible polynomial. So it is already computed in this S box for all possible polynomials. So we quickly do this substitution bytes, and then we are done. This is our new state now. So we take the current state, we leave the first one untouched, the second one we shift left once, twice, and then 3 times. And that's it. So the mixed column, remember that we have to multiply every column to a fixed polynomial, a matrix of polynomials, and then we will compute the B over here. So we would do the same thing with all other columns, and then we are done with the mixed column. The round key, we get the round key, and then you see that we would take them, XOR them, and then write back the results. So you see that the first round, we just add a round key, and then the second round, we do substitution bytes, we do shift rows and mixed columns, and these are the exact values that you're supposed to get after you do all those computation. And remember the last round, we don't have mixed column, right? So it's a different one. So this would be your ciphertext. So this is the part that we didn't cover in our lecture. I think it is easier to cover it on this video. So this is our key, 128-bit original keys that we received from the user, and we need to expand it. And now we are going to see how we're going to expand it. We have a new notation called archon. It is round constant. We are going to add this one. Remember, we have a problem with DES that when everything is 0, all the keys would become 0. So this is one of the ways that they get rid of that entire 0 keys. There are many more ways, but this is certainly one of the ways. So the way that it works is that suppose that I want to generate a word based on the initial key or the previous key that I have. Initially I start with this original key. I go back and I take the previous word, and then I do a rotation. I would use the same substitution bytes, and I would substitute this bytes, and then I go back and I take a word in 4 position behind this word, and I XOR it with the value that I compute, and I XOR it and I added my round constant, and that would help me to create a new word. Just I generated 1 extra word, like 32 extra bits. So once I make that, so the rest of filling this rest is easy. So I just go forward behind, and then I just do XOR with the current value that I have. So see that this XOR would help me to generate these keys very well. So this is the round key 1. And for round key 2, again, I take the previous one, r dot substitutions. The first one is always many operations. And then XOR it at the round key, and I compute this one. So from here, I just XOR it with the previous round key. And that will be enough for me to generate quite random new key. Yeah, so this operation would entirely go around until we find enough number of keys for for that. All right, I think this animation really helps you. If you want to watch it again, you can just search on YouTube AES animation. You can play it many times, and you can watch it for yourself. The only part that you might be a little bit concerned, and I invite you not to be concerned, is this substitute byte and the mixed columns, which had a little bit different computation. And don't worry about it, because this notation of Galois fields would become very easy for you soon once we get to the next chapter. I would have a lot of examples, and we would follow up this computation. How do you compute the inverse? If the inverse is really unique, and all those stuff are things that we're going to discuss there. All right. Do we have any questions? All right. If you guys don't have any questions, today class, so I'll basically upload it once we are done. So I think we have like a few more slides to finish this one. Then I'll upload the new slide to the system very soon. All right. See you guys next week then, if there's no questions.